Hello everyone, my name is Xinhui Lai. I'm from Tallinn University of Technology. Today, I'm going to talk about our research work, which is early RTL analysis for side-channel attack vulnerability in fuzzy extractors of memory-based PUF-enabled devices. The presentation will be divided into the following 8 parts. First, I will explain the motivation, emphasize the contributions of our research work, and introduce the background. Then, I will explain the attack model and attack procedure. After that, the proposed vulnerability analysis will be given. Last, I will show the experimental results and draw the final conclusions. Start with the motivation. PUF represents physical unclonable function. It's popular in the cryptography community due to its inherent variability in the manufacturing process. It's known that PUFs are noisy devices. In order to use them, we need to use error correction mechanisms such as fuzzy extractors. However, recent work demonstrated that applying fuzzy extractors for error correction may enable new opportunities to break the PUFs. For the contributions. In this research work, we have defined an attack model which combines photon injection technique and timing analysis of ECC used for PUF. Then, in order to protect against the attack, we provide an early RTL methodology for verification of fuzzy extractor-based ECC designs. Last, we identified the vulnerability by case studies of Reed-Solomon and binary BCH-based ECC decoder. For the background, I will explain what is the PUF and how fuzzy extractor used for memory-based PUF. PUF is a device that explores inherent randomness introduced during manufacturing to give the physical entity a unique fingerprint. Thus, it can be used to derive identifiers and cryptographic keys. PUF provides a significantly higher security assurance than pre-stored keys, since it is volatile and derived only when required. It also can be easily attached or embedded in the cryptographic implementations. The fuzzy extractor serves as post-processing unit in memory-based PUF-enabled cryptographic schemes. There are 2 procedures, generation procedure and reconstruction procedure. The generation procedure happens only once, as shown in the right-up picture. When you first powering on the device, the PUF will give the unique response, which is the W. Then W will XOR with the encoded code word, which is ES0, to generate the helper data. As for the reconstruction procedure, it will happen at least once during the lifetime, as shown in the right bottom picture. When you repowering on device, due to noise, the same PUF device may give a bit different response, which is W prime. After XOR with the helper data, the error information will be generated, which is ES0 prime. Then after decoder, the initial response W will be retrieved. From the attacker point of view, considering the 2 procedures, it's clear that the ECC decoder in the reconstruction procedure is the most vulnerable part. As for the attack model, we have specified the attack parameters and attack assumptions. Talking about attack parameters, for the physical photon injection to the memory-based PUF, the following parameters are assumed. First is granularity. Each photon injected results in exactly 1 photon in 1 bit data. As for the modification, after the photon injection, the manipulated data is set to a specific logic value. For the control, the attacker has a bit-wise precise control of photon injection to the memory-based PUF bit. The effect of the faults, the injected faults have a transient nature. Following with attack parameters, there are some attack assumptions. First of all, the ECC implementation will leak information through the timing set channel. Second, the internal noise of the memory-based PUF is negligible under the stable environment condition. The errors in the memory-based PUF are caused by the environment. Third, the helper data, which is stored in non-volatile memory, normally remain constant during the reconstruction procedure. Last, The attacker has a controlled access for measuring the decoding execution time. With the above attack parameters and assumptions, the attacker procedure is described as follows. The attack procedure, which is combining photon injection techniques and the timing side channels, are composed by the following 4 steps. First, powering on the device, record the decoding time T. Then, re-powering on the device and inject 1 bit forth at the first bit of the memory-based PUF. Then measuring the current decoding time T1 and compare it with the T. If T1 is not equal to T, it means that the initial value is different from the injected value. If you inject 1, then the initial value should be 0. Then inject forth in the memory-based PUF bit by bit. Repeat above measuring and comparing step until reaching the last bit of the memory-based PUF. And last, the whole secret of the PUF will be revealed. In order to tackle the above attack, we have proposed a vulnerability analysis, which includes structural analysis and simulation analysis. For the structural analysis, here we selected binary BCH and Reed-Solomon as example. For the analysis, firstly, we consider what should be controllable primary input for the decoders. Then we think about how those primary inputs influence execution time for each stage. Start with the binary BCH decoder. It's used for binary bit error correction. As shown in the right top picture, it has 3 stages in total. First is the Cedrum calculator, which is used for generating information for the error bits. If there is no error happens, all the Cedrum should be 0. The next key equation solver, which is BMA, represents Borel-Kermasi algorithm. It will use information from the previous stage to calculate the polynomial function, which contains error position information. In the last chain search stage, it will traverse all the value in the Gauss field and find the solution to the polynomial function. For Reed-Solomon decoder, it's used for non-binary error correction. The structure is a bit different compared with the binary BCH. For the key equation solver, it uses Euclidean algorithm instead of BMA and has additional procedure called phony. Since Reed-Solomon decoder is used for non-binary error correction, thus it has to calculate error position as well as error values, unlike the binary BCH. And for the additional phony stage, it's used to calculate error values. For the structural analysis, we analyze the stage one by one from algorithm. Then we discover there is no time difference exists in binary BCH. Only the Euclidean algorithm stage in Reed-Solomon decoder may require a different number of iterations, which may introduce different execution times. For the simulation analysis, stimulating parameters which may introduce different execution time of decoding iterations are derived as follows. The code word value here represents the encoded code word without errors, the error value, error position, and error number. The relationship of decoding variation caused by manipulating above parameters and vulnerability to propose attack are defined at the following table. Here in the table, C and NC represent the constant and non-constant decoding time, while V and NV represent vulnerable and non-vulnerable to the proposed attack. For the parameter like code word value, it purely depends on the designer, and attacker cannot access to the initial encoded code word, thus it's not vulnerable since attacker cannot modify it. For the other 3 parameters, they can be embedded into decoding code word which has errors. Attacker can modify those 3 parameters through modifying the input decoding code word. Thus, these 3 parameters are vulnerable to the proposed attack. After the simulation analysis, only for the Reed-Solomon decoder, when you input different number of errors, it will generate a different decoding time, and at the same time, it's vulnerable to the proposed attack. For the experimental results, The proposed methodology was validated by running simulation on 3 case study designs, which are binary BCH decoder with serial BMA and parallel BMA, as well as Reed-Solomon decoder. For the 2 binary BCH, we use 12 bits code word and 8 bits message, while for the Reed-Solomon decoder, since it's used for non-binary error correction, thus it has symbols. It has 8 symbol code word for symbol message, and for each symbol, they have 8 bits. The simulation results are shown in the table on the right. It can prove that the binary BCH doesn't have timing channels, while for Reed-Solomon decoder, when it proceeds with different input value, which carry different number of errors, it will cause different timing channels. Here, for our cases, the Reed-Solomon has 3 error symbols correction ability, thus it has 3 different decoding times, and the timing channels are also marked in the table in red. Come to the final conclusions. For our research work, we have defined an attack model based on photo injection and timing analysis of ECC execution that may lead to the secret PUF values extraction. Then, we proposed an early RTL methodology, which includes structure and simulation analysis to tackle the proposed attack. Last, we have demonstrated the timing side channel existence by binary BCH and Reed-Solomon decoder case studies. Thanks for your attention.